Hello Year 12. I know you've got your mock exams coming up very shortly, so I thought I would do a very short video on bonding and do some revision with you and go through the different types of bonding. So what I've done, I've created a revision poster for you to fill in if you feel that you need to, and on the reverse of the revision poster there should be some questions for you to answer. Okay, so I'm just going to switch to my desk cam and we'll go through all the information that you'll need to know. Okay, so we're going to look at the different types of bonding structures we've got, and I've termed them crystal types because I was talking about the different crystal structures each of these made. So the first one that I'm going to talk about are the single atoms. So things that are made from one atom only. So the single atoms tend to be, they're very rare, but they do tend to be the noble gases. So things like helium, neon, argon, krypton, xenon, radon. So they are single atoms. They exist as single atoms. And in terms of their some of their properties, so things that we can measure, like conductivity, can they conduct electricity? Well, they can't, not in the solid, liquid or gas phase at all. They've got no free electrons and they're certainly not charged. So in terms of melting point and boiling point, they're very, very low, of the order of tens of Kelvin. And in terms of the state, they are always gases. So we've got monatomic species, the single atoms, and they're the noble gases. Okay, so the next group we have are the simple covalent molecules. I'm just going to move this along. Okay, so the simple covalent molecules, these tend to be compounds or elements that are from non-metals, so non-metal elements and compounds. Okay, and examples of those would be things like chlorine, any of the halogens, water, H2O, carbon dioxide, HF, so hydrogen fluoride, hydrogen sulfide, ammonia. So simple molecules, but also it's any of the hydrocarbons, the longer chain hydrocarbons that are still less than 10,000 atoms. So we could have short polymers, we could have C60, all of those sorts of things. They would be classed as simple covalent molecules, but I tend to think of them as small molecules, and something that isn't many atoms joined together. In terms of their conductivity, we'll have a look at that. So do these compounds conduct electricity as a solid? No, they don't. Whoops, we'll put across there. As a liquid? No, they don't. And as a gas? No, they don't. For the simple reason that they're not charged and they don't have free electrons. Okay, so their melting points tend to be very low, and the boiling point is very low as well. They do tend to be gases unless they've got more molecules in them, and then they can be liquids or solids. So in terms of the state, we see them mainly as gases, but we can also get liquids and we can get solids as well. The bonding that they've got in there are covalent bonds. Okay, and I'm going to talk about covalent bonds a little bit later on. So I'm going to expand on that, that topic. So I'm just going to put here, atoms are covalently bonded. All right, now you could add in there, in fact, it would be a great idea to add the definition of covalent bonding. So covalent bonding is the sharing of a pair of electrons between two atoms. Okay, so I've added that in. So sharing an electron pair between two atoms. So that's a definition of covalent bonding. Okay, so as I say, I'm going to go over this in more detail in a little bit. I'm just going to so that's one of the second crystal structures. And our third crystal structure is the giant covalent lattices and then macromolecular lattices. And I just want to point out that I've underlined molecules in both of these because molecules are covalently bonded. Okay, if you're going to use the term molecule, then it has to be consistent with you talking about covalent bonding or covalent compounds. So it must have covalent bonding in it to be molecular. Okay, so our next bonding type is the giant covalent lattices or the macromolecular lattices. And again, the clue's in the name, molecular, so it's something that contains covalent bonds. All right, so examples of giant covalent lattices are things that we know already. So graphite, diamond, silica, silicon dioxide, but also some of the biological molecules, the carbohydrates, proteins, lipids, DNA and RNA, they're all giant covalent lattices. And the definition for a macromolecular structure is something with 10,000 or more atoms, different atoms in it. So these are extremely huge structures. So again, looking at those particular things, what can we say about the conductivity of these covalent molecules? Well, in the solid, they aren't conductive except graphite. So except graphite. So that is conductive. When they're molten, again, they are not conductive. In a solution, they don't normally dissolve. So no, they're not conductive. Their melting points are extremely high. So extremely high, high, and so is the melting point. It's extremely high. And the states of these, because of how large they are normally, well, they are solids. Okay, so that's what they are. And what sort of bonding do these have? Well, on them in the main, they have covalent bonding. That is the majority of the bonding. And I just wanted to put in, this is my structure of DNA. Okay, and I'm going to talk about covalent bonding a little bit later on. But this is the covalent bonding that we've got in here. There are other types of bonding in DNA and in carbohydrates and proteins. We do get to see intermolecular bonding, but I'm just talking about the bonding within the molecules themselves, between the atoms. It is covalent bonding. And here I'd like to be able to draw you a picture of graphite and diamond and silica, but I'm not really that talented. So just to remind you that graphite are hexagonal rings, and they are a layer of hexagonal rings. Diamond is a tetrahedral carbon structure, so every carbon is tetrahedrally bonded to another 4 carbons. And the silica dioxide is a diamond structure in that it has it's tetrahedral, but you've got silicon and 2 oxygens attached to a silicon and 2 oxygens. So you're going to get this more open diamond structure, and they're all covalently bonded. Admittedly, within here we've got dative covalent bonding between the silica and the oxygens from neighbouring silicon dioxides. Okay, so that's our third crystal structure. I'm going to clear that away and I'll put my 4th crystal structure down. Okay, so my fourth crystal structure are these metallic lattices. Okay, and so metallic lattices tend to be metals, all metals, and alloys. Okay, so it's all the metals, metals elements, and alloys. Okay, so we see metallic bonding in those structures. Okay, so here's one I drew earlier. So this is my metallic bonding. And I just want to point out that I've got positive metal ions inside this 3D lattice, and the free electrons are in the spaces in between. These metal ions do not touch, and it's a 3D lattice, and it extends infinitely in all directions, obviously to a point where they eventually get to the edges. So we will see this type of bonding in metallic lattices. Now, one of the things with AQA is we don't look at how these metal ions are arranged. I've just shown them uniformly in rows and columns, but we can get a slightly better space saving arrangement of these ions, which we don't study at AQA, and we can look at face-centered cubic crystal structures or body-centered cubic crystal structures, and this is something you could pick up from the interweb, from YouTube. It's quite a simple concept to take hold of, and for those that want to just extend their knowledge a little bit more, then that's probably something I would suggest that you go and look at the different crystal structures for metals and other crystals. Really, X-ray crystallography will really require you to understand the different ways that these atoms can arrange themselves, so that you get a better idea of what you see with X-ray crystallography. And also in the Olympiad papers, they have occasionally wanted you to have some knowledge of those crystal structures. However, we don't need to do that. So this is the representation that we use. The metal ions don't touch because obviously like charges repel, and these sea of electrons are the glue that holds it all together. So what are the properties? So do metals conduct in a solid? Oh yes, they do. When they're molten, absolutely, definitely. And when they're in solution, well, actually, they're not soluble. Okay, so they're not soluble. In solution would suggest in water. Metals don't conduct, well, are not soluble in water. Melting points are, well, they're high to very high, high to very high, and that's the same with the boiling points, high to very high. And the state for metals, they're all except one solids, and the one that isn't a solid is mercury, which is a liquid. It's the only one that's a liquid. Okay, so that's the fourth crystal type, and we're now going to look at the fifth one. Just before I move on to the fifth structure, I should have mentioned what are the forces of attraction between here, and we need the definition. So the definition is that we've got electrostatic forces of attraction between the positive metal ions and the sea of delocalized electrons. So that's the definition of metallic bonding: electrostatic forces of attraction between positive metal ions and a sea of delocalized electrons. Okay, so now I will go on to that fifth crystal structure. Okay, so here we are, we're looking at our fifth crystal structure, which is ionic lattices. Okay, so where do we find ionic lattices? Well, that is between metals and non-metal, non-metal I could spell it right, non-metal compounds. Okay, so they are metal and non-metal compounds. Metal, non-metal compounds. Okay, that's what they are. And in terms of the bonding that we see between them, it's an electrostatic force of attraction between oppositely charged particles. And here's a particle diagram that I have drawn. So we can see that we've got alternate positive, negative ions that are touching because they're attracting each other. And we've got these alternate positive, negative ions, and it's a 3D structure. So I've tried to show that it's 3D. So it extends in all directions infinitely. Well, obviously till the end, till you get to the edge of the crystal. So in terms of their properties then, so let's have a look at the properties. Do ionic lattices conduct electricity? Well, not as a solid, but when you melt them and they become molten, then yes, they do, because those ions become free to move, just like in a metallic lattice. When it's molten, the ions are free to move, and because they're free to move, they will conduct a charge, and so we will get conduction of electricity. And then in solution, will it conduct electricity? Yes, it will. These will dissolve very easily into water, and once they're dissolved in water, the charges become free to move, and a charge can then be passed through. In terms of their melting and boiling point, they are high. They are very high. Just so extremely high. So extremely high. In fact, some of these melting points and boiling points can be higher than metallic lattices. Extremely high. Okay, so the size of the melting point and boiling point gives you an indication of the strength of the bond. So what state would these be in? These are usually in the solid state. Okay, they're in the solid state. And as I was saying, the strength of the attractions between the ions can be measured by the melting and boiling point. So when you compare melting and boiling points from one bonding type, from one crystal type to another crystal type, then you can get a good idea of the strength of those particular bonds in those compounds. So I'm going to have a look at the simple covalent molecules in a little bit more detail. So they're the bonds that are made between non-metal elements and compounds, non-metal compounds. And I just wanted to remind you of how we represent the shared pair of electrons. So first of all, we've got the Lewis dot and cross structure. So dot and cross diagrams, they're also called Lewis diagrams. And we can show that the electron pair is being shared between two atoms here, and we can see the overlapping orbitals. Another way of showing that is using a ball and stick diagram, and that's a nice way to look at those covalent bonds. Also, what we can do is we can do like a shortened version of the Lewis dot and cross diagram. So we can just omit the orbital and just put the electron pairs between the two atoms. So this would be oxygen, the double bond between oxygen, and you can see the crosses that have come from one atom and the circles that have come from the other atom. And we can also show covalent bonds just as lines. So it's a bit like this ball and stick diagram. We just get rid of the ball and we've just got the sticks in between. So this is nitrogen with its triple bond. And then there's another way of showing the covalent bonds, and it's another model really, and it's this electron distribution, this electron cloud distribution or electron density around two atom radii there. So there's different ways of modeling these covalent bonds, and we have become quite adept at picking whatever model we want in order to be able to explain what we want to explain. And this is the beauty about chemistry. We do have a number of different models. Some work better than others. And what we're going to do now is we're going to look at these covalent bonds, and we're going to see how the electrons are shared between those atoms. So I'm going to use this electron distribution model to help me to explain that. So this is the quantum mechanical model. So this is using mathematics to predict the likelihood statistically of finding an electron, and this cloud is supposed to represent whereabouts we would find that electron. Now, if these were the same atom, so let's imagine it was say hydrogen, for instance, or it could be iodine, any one of those. The electron pair we always think is shared in between those two atoms, equally in between, but actually it's not. We've got this electron cloud that is distributed all around or between both atoms, and actually when we look at this, we can see that localizing it between the two atoms is possibly, it's all right, it gives us a good model to work with, but when we're thinking about intermolecular forces, then this is not going to help us a great deal. And imagining that the electrons are smeared around the two atoms is better than this one where we see them localized. So if we use this, then there's going to come a point when we could imagine that the electron, when we take a picture, we would find that the electrons might be to one side of the atom. When we take another picture, we could find that the electron is evenly smeared between the two. Or we could take a third picture and we could see that the electrons are smeared towards a different side. And we're going to get this transition, particularly if these are atoms of the same element. So if this we'd normally see in the same element. So this would be something like hydrogen or iodine or chlorine, nitrogen, oxygen. And if we've got electrons more to one side, then that's slightly more negative than this side. So overall, this molecule is neutrally charged. There's no charge to it. But if we can imagine that the electron cloud goes to one side, then we've got slightly more negative charge on one side than the other. Here we've got an equal distribution, so there's absolutely no charge on here. And then with this one, we can see that most of the electrons are on one side than on the other. So what we've got is we've got dipoles set up. A dipole is where you've got separation of charge, of opposite charge. So we've got a dipole, and we can see that this is only temporary. It goes from one side to another. It could be at any point. So we call these temporary dipoles. And actually, these temporary dipoles, when they act between molecules, say molecules of hydrogen or molecules of chlorine or molecules of fluorine, we call these van der Waals forces. So van der Waals, and these are temporary dipoles. Okay, so this is where we've got atoms, the same atoms that are bonding together. What about when we get atoms which are not the same, like hydrogen and fluorine, for instance? So here I've got a representation of hydrogen and fluorine, and they share a pair of electrons, but one of those atoms will share those electrons a little bit more than the other one. And this is electronegativity. So we've got an attraction for the bonding pair of electrons. And just from an electron cloud point of view, this is what it looks like, and it permanently looks like this. So the electrons, the electron cloud is going to be pulled more towards the electronegative element. So that's going to be the electronegative side. So that will have a slight positive, negative charge, and it'll leave a slight positive charge on the other side. So if, as I say, that was something like hydrogen fluoride, and here's hydrogen fluoride, we can represent that delta minus and delta plus as slightly positively charged and slightly negatively charged, and it's permanently like that, and we call that a dipole. And we can actually draw that permanent dipole in as it is. So this is called a permanent dipole. Okay, but we also term that a polar bond. So it's a permanent dipole, but we also term it a polar bond. So polar bond. Okay, because it's got a polar bond, it's got a permanent dipole. That means the electrons are pulled to one side, and we can represent that dipole by this arrow and cross. Okay, we can show that it's slightly positive on the more electronegative element, and slightly more negative on the electronegative element, and slightly more positive on the less electronegative element. And we can look at the different types of bonding in between the molecules. In our temporary dipole bonds, we called those van der Waals forces, because we're going to get attraction between positive and negative ends of the dipole, or if we've got a dipole already created, we'll induce a dipole in the next atom, next molecule, and so we'll create these transitory van der Waals forces. But in these, where we've got a permanent dipole, then we're going to get more permanent attractions. We're not going to get transient attractions at all. And I just want to represent the type of intermolecular forces with hydrogen chloride. So we've got a gaseous mixture of hydrogen chloride, and we can put in our delta negative, delta positive, because we know we've got a dipole on here. The chlorine will pull the electrons, and we will get some lining up of our molecules. So we can draw a representation of the intermolecular forces. We've got a delta negative here, and it would align itself with the delta positive. So you could see that you're going to get some order occurring in here. This delta positive and this delta negative positive here, well, they wouldn't. What would probably happen is that may push that away or spin that around. But we can see we've got attractions here, or we could get attractions there. I can put in more HCl, and we'll get attractions at that point. So we've got these intermolecular forces of attraction, which we call dipole-dipole attractions. So they're across space, they are between molecules, and they're a little bit stronger than the van der Waals forces, which are transient. So these are our permanent, I'm going to call them permanent dipole attractions. Now, we've got a special case of these permanent dipole attractions, and there's only a few molecules that show that attraction. So those molecules are on the top row, and it's nitrogen, so NH3, and they've got double bonds, a pair of electrons. We've got water, H2O, and we've got two pairs of electrons there. And then the final one is HF. HF. And with HF, we've got 3 pairs of electrons. Now, of all the molecules that we have, these show a particularly strong attraction between molecules. So with all of these, we have polar bonds, we've got permanent dipoles. However, what we do have is we've got stronger bonds occurring between the lone pair of the nitrogen and a hydrogen on the nitrogen, and that creates for us a stronger dipole-dipole attraction. And similarly with water, we've got 2 lone pairs being attracted to, or the negative end of water has got 2 lone pairs, and they're attracted to the 2 delta positive hydrogens, and so we're getting stronger bonding there, and we've got 2 hydrogen bonds in water. With fluorine, we've got 3 lone pairs of on the fluorine, and there one of those is attracted to the hydrogen, the delta positive hydrogen, so we're getting 1 hydrogen bond in HF. So we get hydrogen bonds between N and H, and any H that's attached to an N. We between H and O, between a H and any H attached to an O, and between H and F with the H attracted to the F that's attracted to a, that's got on a HF. So it is only between these molecules. If we get a mixture of these together, then they will hydrogen bond with each other, because they ammonia will hydrogen bond with ammonia, but if it's in water, it'll hydrogen bond with water as well. And if HF is in water, it will hydrogen bond with any of the waters, as well as hydrogen bonding with itself. So these will hydrogen bond between each other, but they won't hydrogen bond to any hydrogens that are attached, say, to a carbon or to a phosphorus or a sulfur. They only hydrogen bond with each other, and these are particularly strong. Okay, so typical questions that you get asked on these bonding examples are about usually predicting which has got the greatest melting point, putting them in melting point order, and that's to see if you understand the types of bonding that you've got. So here in hydrogen chloride, we've got permanent dipole attractions, which are fairly strong. So we'd expect to put a little bit of effort into being able to break those. Whereas here in hydrogen fluoride, we've still got permanent dipole, and we've got permanent dipole attractions, but we've also got hydrogen bonding. So we know that with this, we've got particularly strong bonds, so that we're going to take a lot more energy to break the bonds in hydrogen fluoride. And then in iodine, iodine is a solid. It's one of the few, well, it is a halogen that's a solid. And why is it a solid? Because it shares its electrons equally. Well, with iodine, we have these temporary dipoles, and they induce dipoles in the other iodine molecules. That's why I've written here temporary dipole, induced dipole. And there are van der Waals forces. Usually we recognize them as quite weak, and they won't take an awful lot of energy to break those bonds. So we would then, we could look at something like that. And look at the meltings and boiling points. However, if they give us melting and boiling point data, then we can have an idea of how strong these bonds are. Or you may be given a structure like this, where you've got ionic compounds and metallic compounds, and you'll be given a boiling point for each of them, and you would be asked to describe why one has a higher boiling point than the other. And the reason for that would be that it's got stronger forces of attraction between, and in this case it's between either oppositely charged ions or between the iron and the sea of electrons. So the boiling point gives an indication of the strength of those bonds. So typical exam questions do tend to ask you to compare and to explain. And in some cases, you may think that the boiling point that should be very, very high for something like this ionic compound here. But if you're asked to compare it with something like diamond or graphite, the boiling points are going to be very, very different because the strengths of the bonding is different. So we may think that this has got a high boiling point, it's very strong, but when we look at the boiling point of, say, graphite or diamond, the boiling point is higher because we're having to break more bonds. So we've got more bonds here to break, and so this is going to give an indication of the strength of this lattice in total. So again, that comparison and being able to explain it. Well, that was a bit of a whistle-stop tour of bonding. So I hope you've been able to fill in the revision mat and that you're able to answer some of those revision questions. I'll also provide you with some typical bonding questions for you to have a go at and the mark scheme. Okay, so good luck with those mock exams, and don't forget to consider the bonding. Thank you.